Challenge. Bismillahirrahmanirrahim. Let's get started. It's just be a short lecture today, and so we have so that we have covered some important points. What did we do last time? Very quickly. C तो close कर दिया था. उससे पहले Laplace
कंपैरिजन किया था इससे.
comparison and what was the main thing? Going from discrete time to continuous, right? And what happened? N became
T.
T,
Yes, sir.
right? And
Sir, Z raised to power n became e raised to power
ST, right? So the eigenfunction of a dt LTI was now this guy,
Yes,
and
Summation
summation
became integration.
integral, right? And this naturally led to everything else. कोई उसमें हमने we didn't do anything special, yeah. So I won't repeat that. The only thing I want to write now, what it naturally leads to, is the z transform, which was xn z minus n. ये तीनों चीजें यहाँ हैं, देखें, yeah. In one formulation, all three are there. How is that? N becomes t, right? And z minus n is replaced by e minus st, summation replaced by integral, and you have Laplace transform, right? So, and of course now this z becomes what we call s, right? So it is xs, the Laplace transform is the integral of the time domain in continuous function with the eigenfunctions and dt and minus infinity to infinity if it's bilateral, and 0 to infinity if it is unilateral, right? And then we discussed several other aspects of this, but briefly speaking, what did we do for we found the Laplace transform of three functions, if you remember. कौन से functions थे जिनका हमने Laplace किया last time? It was the same as what we had for z transform, right? Very similar. So delta t had a Laplace of unity, right? And then our region of convergence associated with each one. And then we had our other favorite, the ut, right? Unit step. इसका क्या आया था? 1 over s. Okay. And then we had e minus at ut, right? इसका क्या आया था? 1 over s plus a. Right? So these are very important ones. If you remember, delta n had 1, un had z over z minus 1, and z minus m times ut क्या था? This thing, was it this or gamma minus m? I think it was. Yeah. Something like, yeah, it was. So it was z over z minus m, something like that, if you remember, right? So just like this shows here, it was showing over there, or we can verify, maybe it was slightly different, but so although the form may look a bit different, but the methods are very same and the concepts are very similar. Now, what do we have left now? These are some pairs, and I ended by saying that next time we will just look at a few properties of the Laplace transform. Interestingly, they are very similar to what you have seen for z transform. So I'll just mention a few and you can see the rest in the book. Firstly, as before, it is linear. So what does that mean? That means that if there is an x1t that has Laplace x1s, and there is another x2t that has Laplace x2s, then alpha 1 x1t plus alpha 2 x2t has Laplace, which is similar linear combination of the original Laplaces. Yeah, so what is it? Alpha 1 x1s plus alpha 2 x2s. It's very helpful because it helps us take the Laplace of separate terms separately and then add them up in the solution. Yeah, right. So this is linearity. and this you have also seen for Z transform. Time shifting. किसी को याद है time shifting for Z transform we had? What happens in Laplace? If xt has Laplace transform xs, then if you shift in the time domain, that leads to the original Laplace being multiplied by this guy. और exactly यही हो रहा था in discrete time. If you remember, if you shifted xn minus capital N, you had a multiplication with z minus n. Yeah. So same thing is happening here. Nothing new in there. Then yeah, skip the frequency shift. Is same to Z transform. Or one more that is very useful is the differential. Okay, so dxt by dt. What's the Laplace of this? The Laplace of the derivative. If xt has Laplace xs, then the derivative of xt has Laplace s times xs minus an initial condition, which we usually skip in the formula just to make it simpler, but this is how it is. The derivative in time becomes a simple product in frequency, okay, sxs minus an initial condition. इसी तरह second derivative क्या होगा? Second derivative will be, interestingly, it is s square xs minus s with initial condition, first one, and then second initial condition. आपने solve किए second order differential equations? What do you need to solve second order differential equation? You need two initial conditions, x0 and x dot 0. याद है? For discrete time, we were talking about initial conditions x0, x minus 1. That was discrete time. Continuous time mein you talk about x0, x dot 0. That means what's the value of the differential at this thing. Similarly, if this was cube, you will have s cube xs minus s square x0 minus x s x dot 0. So it just keeps shifting. वो आपने memorize नहीं करना, but it's just a pattern that shows up, and it has serious implications. Now, interestingly, what about the integral? What happens to the integral? So, if कोई guess कर सकते हैं integral क्या होगा? Derivative becomes sxs. Let's say initial conditions are 0, right? Then it's very simply, if you had xt corresponding to, in the Laplace domain it looked xs, then if you take the derivative of xt in time, it became sxs minus some initial conditions. If they are 0, it's क्या हुआ था? Simple multiplication with s हो गई थी, right? अब इससे आप guess कर सकते हैं इंटेग्रल के केस में क्या होगा. अगर मैं let's say इसको to some range इसको इंटीग्रेट करता हूँ, original function in time became xs. If I took the derivative of that, it became a multiplication with s. What if I had taken integral of this? Guess. Divide by s. क्योंकि टाइम में अगर आप दोनों ऑपरेशन करें तो वापस आ जाता है, तो फिर 1 by it makes sense, doesn't it? So what happens here? Notice, remember what Z transform did to difference equation? It converted it into simple algebraic equation. Now notice what Laplace transform is doing to differential equations. Derivative को product बना देता हो, integral को division बना देता है, simple algebraic हो गया, right? And we will come to that later in more detail. Then there is the one more I want to mention. You already know what happens to convolution. I don't have to tell you every time, right? So if we had convolved two functions in time domain, what would happen to their Laplace transforms in frequency? Simple, product, right? So it will be just this. ये तो we have really gone in great detail when doing the discrete time. Same thing holds for continuous, so we don't have to develop it from scratch. एक नई चीज जो हमने discrete में we did not cover that. This is called initial value theorem and final value theorem. Okay, we won't do the full theorem. We will mention the result, which is very useful, and that is like this. Let's say you have a function xt and you want to find its initial value, which we call 0 plus, just 0 से थोड़ा सा ऊपर. Okay, just as it mathematics में continuous variable है, so 0 plus means just after 0, the very first value it will take, and then we are interested in x infinity. Okay, so often when we are working with the frequency domain, it helps actually to know this rule that SXS. If you want to find the initial value of a function in time, there is another way to do it. You may say, okay, why not do it here? Often this is not possible to get these. Function may be defined in such a way, it's not easy. So what you do, you take it in the Laplace domain and find it there. Okay, so what does that say? It says if you want to find this, all you have to do is take the Laplace transform of your original function. Maybe you already have it in some form. Multiply the Laplace with an s and then set the limit s goes to infinity. If you solve this, if this limit exists, that will be the initial value. What about the final value? Any guess? From symmetry. S, I can tell you it's Sx here, but what about here?
Limit s to 0.
Yes, good. Symmetry has beauty to it, yeah. So 0 becomes going to infinite, and infinite, that is the final value, we call it. The final value can be obtained by setting this to 0. Okay, so I'm not proving this theorem, these theorems, but yeah, they are useful sometimes to find the initial and final values of functions or signals. Yeah. Now, as I mentioned already, we saw that discrete time LTI systems could be modeled as difference equations, right? For example, we were able to say, okay, one discrete time dt LTI system may look like, let's say, this. Yeah, this is a difference equation. What it is? It's a weighted or linear sum of some past input and output. हमने इसका बहुत general form भी किया था, right? What did we do to solve this? I have shown you this before, that if you try to solve it here with the initial condition, let's say if you know the initial condition, or if it is 0, it's easier, but you will have to solve this iteratively. Yeah, with the help of Z transform, however, what did we use? There was this thing called xn minus k, that is z minus k x z. ये याद है? Right? With the help of this, we were able to solve this very easily. Let's say this problem is with initial condition 0, just to simplify our work here. If I take the Z transform of both sides, what do I get? Y n minus 1 has Z transform, Z minus 1 y Z. This I can take to the left, right? And if I do that, I have yz equals 3xz divided by what? Quickly. 1 minus 0.8 z inverse. Yes? And I have shown you this. If you know the input, you can put its z transform here, and then you can do partial fraction expansion to solve this, and you have your output. Okay. So, and usually you do it with the help of tables or computers. But what happens now is that the output became a simple product. Let's call this hz times xz. What is hz here now? It's 3 over 1 minus 0.8 z inverse, right? So a difference equation became a simple algebraic equation with multiplications, divisions, and such. No delays or anything. Yeah, which means you don't have to solve it iteratively now. Yes, the same thing. Same thing. This is just a repetition. We did it in great detail for discrete time. Now the same thing happens in continuous time, but with what? Laplace transform. And with difference equation replaced with what? Differential equation. So, firstly, we will say that CT LTI systems can be written as differential equations, okay, which involve differentials of the input and output. That's one thing. Second, using Laplace to convert these to simple algebraic equations. And then third, solve those and do reverse Laplace and get your output. So it's a complete exact counterpart or analogous of this thing. Whatever happened here is going to happen now in discrete time. And what is going to help us? In discrete time, what helped us was this property, right? In continuous time, क्या चीज help करेगी हमारी? Knowing what this thing, the kth derivative, अभी मैंने आपको एक दो derivative बताए थे of yt. If you take the kth derivative of yt, then in Laplace domain, this is what happens. There are minus several initial conditions, but if they are zero, it can be simply written like this. यहाँ पे the magic key was this, okay, in discrete time. In continuous time, this is the magic key. This formula is going to help us convert discrete continuous time differential equations. So let's see. Now, very parallel to what we did here. Let's say if we have 5 dyt by dt plus 6 yt equals 4xt, and let's say I assume all initial conditions are 0. I don't have to, but it just reduces some terms. It's easier to write, and I just want to bring home the point. Now, can someone help me convert this? Is it a differential equation, by the way? It is. There is a differential here. If I could get rid of the differential without bringing in an integral, usually when you try that to bring in an integral, then it is again a differential equation in the form of integral equation. But with Laplace, you can help me convert this into simple algebra.
Yes, sir.
Okay, so how does it begin?
So
There is 5.
5
Use that.
y
S
y s
Okay.
SYS, because the first derivative, so the power is 1,
1.
and there was supposed to be minus y of 0, but I said all initial conditions are 0, so we don't need to bother about that.
Put the remaining
Plus
values in.
6y s equals 4x s.
Yes, sir.
Now, what does this lead to? You can take the ys common, and this will lead to 4 over 5s plus 6xs. Just like, see, it's now this product of hs, which is this thing, times xs. And you know, even without special partial fraction expansion, you can just use the inverse Laplace table to actually simply write it directly. You will, to get the full thing, of course, you need what xs is. You have to put that here and then solve the whole thing, right? But it's usually faster. But notice, right here already, what happened? No derivatives, no integrals. right? Simple algebraic equation. Now, tell me this: have you seen anything like this before?
The differential equation.
Differential equation converting into a algebraic equation? No.
Substitution.
Substitution, like when solving differential equation, what were you substituting with?
So usually maybe a u or t, a variable.
Yes.
Okay, so what about have you seen this linear differential operator D?
Yes. Yes.
Were you ever taught that
d
dy
prime.
t
Yes,
by
yes.
dt we will write it as
A capital
d
Yes.
y?
Yes, sir. Yes,
Were you taught that?
Yes, sir.
And then you were taught that d square yt dt was d
As d
square
prime.
y.
D square. Yes, sir.
Right? Without teaching you Laplace, they were teaching you to use it. यही है ना?
Yes, sir. Yeah, yes, sir.
Yes.
Okay. आप वो कर रहे थे. You were converting differential equations, but how you were doing it? By putting this d operator here. Right? फिर आप क्या करते थे? फिर आप उसको once you had written that as an algebraic equation,
Yes, sir.
you weren't using inverse Laplace because you weren't taught that by then. But indirectly आप कर रहे थे use inverse Laplace. What you were doing once you had written in terms of d operators, आप d's को इकट्ठा करके ऐसा कुछ बना लेते थे,
Yes, sir.
right? 4 over 5d plus 6 or something, yeah. And then you were told, okay, we have an idea. Either you did partial fraction expansion, जो भी पढ़ाई जाती है, I don't know आपको पढ़ाया कि नहीं, but otherwise you were told that there are special solutions in the form of e minus alpha t. कहते हैं ना c1 e minus alpha t plus c2 e minus alpha 2, आप कहते हैं c1 और c2 फाइंड कर लो. वो जो c1 e minus alpha 1 t है ना, वो actually they are taking from the, ये जो मैंने आपको फॉर्मूला बताया ना, कहाँ गया वो, ये वाला, let's see, is it here? Yeah, this thing. 1 over s plus a corresponds to e minus at ut. ये हमने किया था ना? So they knew that you will end up with some sort of partial fractions and each one can be solved like this. तो आप कहते हैं कि solution आपका will be like c1 plus c2. Now just alphas will come from the roots and c1 c2 you can find by tricks, solving some tricks, yeah. So this is a well-known approach used in mathematics in solving integral and differential equations, okay. And whether they tell you or not, what they are actually using is the Laplace transform, okay. So you have seen it before, you will see it again in circuit analysis 2.
Sir, we
कर
have
लिया?
done that.
कर लिया?
Per-
उसमें आया था ये?
Yes, sir.
When you wrote an RLC circuit,
Yes, sir.
Yes, sir.
by definition RLC circuit becomes a second order differential equation.
Yes, sir.
So what did you do?
So
You
we
did
used
something
Laplace.
like this,
Yes,
but without maybe going into full detail, or maybe you did. But you have already seen, as I said, in the form of D operator. Without naming it as Laplace, you had seen it there, okay. So I committed that this will be a short lecture, and I see, yes, we will do the rest, the more general case of this,
Yes, sir.
inshallah, next time. Friday we can discuss that,
Yes,
right?
sir, the
Session.
podium,
Okay, we can discuss that. So
To my side.
before that, so for the sake of recording, any questions from this?
No, right
I went a bit fast because, as you know, I mentioned the underlying concepts we have done already. I am just mapping from discrete to continuous, right? So I have this luxury of going a bit faster, but that doesn't mean that you have to grasp it at that speed. You can ask me to repeat, or just watch this and then come back to me. Right, so we'll stop it here.